Okay, so there's where we left off last time. We had talked about how these sine and cosine waves, particularly in a crystal, so we're considering here now, for example, electron density waves, so some component of the electron density, which corresponds to this Fourier representation. So we've got waves, not moving waves, stationary waves, in these two different directions, corresponding to 5, 5, 0, and 5, minus 5, 0. If you count crests along the edge of the unit cell, which has this orientation as shown down in the corner. All right? So when you combine, just for example, those two waves, you end up getting a constellation of peaks. So we could imagine these to be electron density peaks. Ignore the negative part of it. We could say, okay, this is kind of a representation of an elemental crystal, a metal, for example, if we want to imagine something specific. And we said it can be more complex when you combine more, or you can get a more complicated surface by combining more and more of these waves. And in general, when we're mapping you've seen perhaps projected electron density maps, which kind of resemble this. They're isocontour maps. But they can be representing quite a complicated molecule, so that means corresponding to this isodensity contour map, or two-dimensional representation, we could have a relief map, this kind of three-dimensional representation, and this could represent some kind of a low resolution picture of some macromolecular crystal structure with the red net, mapping the electron density. Oops. That was telling me to finish. Now the next thing we want to remember is that these Fourier terms, we looked at the foundation of the Fourier series at the beginning of, or somewhere in the middle of the last class, that these involve complex exponentials. Exponential 2 pi I h dot x k plus k dot y plus l dot z, that's the form that we had, or exponential minus 2 pi I, okay? The two different Fourier transform representations, that for the structure factors, f has in its kernel exponential positive 2 pi I, and that for the electron density, or the scattering density, has in its exponential e to the minus 2 pi I. You could turn that around. They have the two components, so the forward and back components, have to have kernels, complex exponential kernels of opposite sign. It's just a convention which is which. I choose to follow and many crystallographers choose to follow the convention, thinking that we're talking about electron density. Okay, electrons have a negative charge. So for the electron density representation, we choose exponential negative 2 pi I. That means in the structure factor expression, it's exponential positive 2 pi I. But we'll be going over that kind of thing again. So here we're looking at the family of numbers. In the most general case, we have outlined here the complex numbers, but in the simplest case, we just start with the counting numbers, the so-called natural numbers, indicated by this kind of bold N. Then we add to that list negative numbers, okay, so we can have integers, positive or negative. It was a big discovery at one point in the history of mathematics to think about the number 0, which was not a counting number. So there was a hurdle to get over to generalize to the integers. Then generalizing further, any of the integers can be represented by rational fractions. So a fraction with an integer numerator, integer denominator. So this is a larger family of numbers. There are, between any two integer values, an infinite number of rational numbers, but then there's an even larger infinity of complex numbers. What we mean by algebraic numbers are those that can be roots of a polynomial equation. So there are some numbers, as we shall see in a moment, that are not algebraic. And those are the ones that fall outside this area. So here's algebraic numbers, which include rational numbers, integers, natural numbers, and zero. But if we consider then all of what can be complex numbers, denoted by the boldface C, that embraces everything. So we have the imaginary unit here, I, which holds a status comparable to zero for the real numbers, for the algebraic numbers. We have to include these complex values because polynomial equations can have complex roots. So it's kind of a numerical hierarchy. And we need to be willing to work in the largest sense in that hierarchy because we're dealing with series expansions that will have, in general, complex valued terms. In general, the structure factor is a complex number, has a real and an imaginary part. The electron density, it turns out, is a real number, and that's one of the things we'll be wanting to show when we talk further about some of the basics of X-ray diffraction theory, that although the structure factors are in general complex values, the electron density is real valued, and showing how that happens is one of the exercises we'll get to. Okay, so complex numbers. This is kind of reviewing from your, I guess, high school mathematics. The imaginary unit I is the number that has the property that its square is -1. The reciprocal of that imaginary unit is the negative of the unit. And if we multiply I times minus I, we get negative the square of I, or 1. These properties of the imaginary unit. And then complex numbers, we can represent them as x plus iy, or in polar form as their magnitude z times exponential I phi, or the magnitude z times cosine phi plus I sine phi. Here we have the Euler relationship, which is one that's centrally important to everything we do in electron density and structure factor representation. Okay, so the magnitude is the square root of the sum of the squares of the two coefficients, the real coefficient, the imaginary coefficient. The phase angle, or phase, or sometimes called argument of a complex number, is the arctangent of the ratio of the sine of this angle to the cosine, or the arctangent of the ratio y over x, and so on. There's a real part and imaginary part. So one of the things we'll be doing is considering complex numbers and their conjugates. And no matter how complicated the complex number is, maybe it has many terms in this, maybe it's an expression for y with many terms. So there could be many terms in here with coefficient I. But to get from the complex number to its conjugate, you simply replace I by negative I everywhere it appears in the complex number. So for example, an expression for a structure factor, we might have thousands of terms, one for each HKL triple of integers, a set of indices, and so that means a sum of thousands of complex numbers, but the complex conjugate of that is just given by everywhere I appears, turn it to minus I. And the complex conjugate is generally symbolized by putting a star. So z star is x minus iy, given that z is x plus iy. So that's the Cartesian form. So on the xy plane, the Cartesian xy plane, on the polar plane, we have a magnitude and a phase, rotation, angle, phase, and the trigonometric form, the e to the I phi part of it is replaced by cosine phi and I sine phi. And the squared magnitude is the product of the complex number. So what do we mean by saying the square of a complex number? What we mean is we multiply the complex number z, in this case z, by its complex conjugate. That's the square of the magnitude of this complex number. And then we have the conditions for equality. It's the real parts equals the real part, and the imaginary part equals the imaginary part, so these two different, and so on. We can add these things just by normal algebraic addition. We add up the real components and then add up the imaginary components, or the coefficients of the imaginary components. We can multiply these numbers together in the way we usually multiply binomials in algebra, and we can similarly do the division and express the division either in Cartesian terms of the form x plus iy, or in polar terms of the form radius e to the I phi. In this case, since we're doing a division, a subtraction of the polar anchors. Okay, so the wonderful and central thing in all of this is the discovery by Leonard Euler. Well, he wasn't the only discoverer, but he was the one who realized that's Nate. Hi, Nate. Okay, so we recovered. We couldn't get the projector to say, okay, I'm warmed up and let's start, but finally we did. Okay, we're good, thanks. So this wonderful Euler formula, e to the I phi equals cosine phi plus I sine phi. Richard Feynman, the Caltech physicist, Nobel laureate, who wrote this wonderful, or presented this wonderful series of basic physics lectures to the Caltech. I think they had a 4-semester sequence, a 2-year sequence of basic physics. I think everybody at Caltech has to go through that course. Anyhow, in his wonderful Feynman lectures on physics, which have been published now in book form, and are a pleasure to read, his insight and his ability to explain what's going on in physics, and his facility in mathematics without snowing people with a complicated mathematics, it's all just remarkable. But anyhow, Feynman's remark during one of his lectures when he came to discussing this with his students, or showing the Euler formula to his students, he called this equation, this formula, the most remarkable formula in mathematics, and referred to it as a jewel, as a physicist's jewel. And I think that's a very apt description. So from this formula, if we consider the case that phi is equal to pi, okay, e to the I pi, well, the cosine of pi, cosine of 180 degrees, is unity. Okay? And the sine is equal to -1, and the sine is 0. So if you just move things over to the other side, we get the so-called Euler identity, a beautiful mathematical object, e to the I pi plus 1 equals 0. And Gauss, who was one of the ones who set mathematics on the right road to dealing with complex numbers, some credit him with the invention of the, well, as we saw in the last, the invention of the so-called Argon plane, where on the horizontal axis, customarily we call it the x-axis, we represent the real part. Some length along the x-axis is the real part of a complex number, and along the vertical axis, which is the imaginary axis, represent the imaginary part, some distance along the vertical axis represents the y part of x plus iy. So we have this planar two-dimensional representation of the complex number. So Gauss, who apparently was not necessarily a warm and fuzzy guy, reportedly said that anyone to whom the Euler identity was not immediately obvious could never be a first-class mathematician. Well, it didn't become obvious to Richard Feynman until he was about something like a freshman in high school or just finishing junior high on Long Island. He was brought up on Long Island. And at that time, while all the other boys were just fascinated with girls and their development, Feynman shared that interest very vigorously, but he was also keeping a diary in which he wrote out and then discussed the Euler formula and the Euler identity. So at age about 12, he was thinking about this deeply meaningful mathematical relationship. The mathematicians, the philosophers of mathematics, talk about the Euler formula as having deep mathematical meaning. Deep becomes a kind of technical term in mathematics. So it's so fundamental that much of mathematics just builds on it. And the implication of this deep mathematical meaning is this unification of algebra and geometry, because you have now the complex exponential function linked to the trigonometric functions. And we can always compute, we can always define the trigonometric functions, the cosine and sine, in terms of the complex exponentials. Just add these two equations. So this complex number, and here its complex conjugate, sum them and form their sum and difference, and then divide out by 2, you get the cosine and sine functions. So one of the mysteries that Feynman was contemplating along with girls is the beauty of this Euler identity, because it links the real numbers, the two most important of which are 0 and 1, or 0 and negative 1, to complete the real numbers from the counting numbers. This is what had to be added, was 0 and negative values to get from the natural numbers to the real numbers. And the transcendental numbers, pi and e, and then the imaginary unit I. Transcendental numbers are numbers which are not the roots of algebraic equations. So there's a lot of meaning, a lot of beauty in thinking about these relationships. So let's think about Euler's number E. I'll talk a bit about Euler's number E. How is it defined? Well, it can be defined in several different ways, but the most commonly used one is to say that E is the value of this infinite series, right, summing from 0 to infinity, of 1 over n factorial. N factorial means n times n minus 1 times n minus 2, and so on, all the way down to 0. N is a real number. So that and the limit, the value of this infinite sum, okay, summing over 1 over n factorial, for any unlimited numbers of n, the limiting value of that sum is this expression, 1 over 1 over 1 plus 1 over n. As n gets larger and larger, we get closer and closer to the value e. So e is a real number. It's not itself a complex number. It's a real number. But it is not a rational number. Right? It doesn't belong to the set of rational numbers. And it is not an algebraic number. It doesn't belong to the set of algebraic numbers. That is, e itself is not the root of any polynomial equation. Okay, so it has the numerical value, 2.71828, and so on and on and on and on, and it goes on in principle forever because it is not a rational number. It cannot be expressed as a ratio of integers. But this is a fair enough approximation for any of the hand calculations or even computer calculations that we'll be doing. Of course, people have worked out its value for I don't know how many decimal places now, millions. There are computers who spend much of their time doing things like evaluating pi and e to, or the square root of 2 and so on, to many, many, many decimal places. So the E number, the Euler number, has this interesting property that if we plot it against a real numbers axis, okay? So that means that the plot of this function goes through the point x equals 0, y equal 1. And then it also goes through the point x equal 1, y equal e. So this is the behavior of the exponential function, y equals e to the power x. Now this second panel, which is showing the same thing, okay? This is the point x equals 0, y equal 1, and then over here someplace is the point x equals 1, y equals e. But that make it happen. Yeah. So this is how this limiting function behaves. It's supposed to repeat itself. As n increases. So you see that as n increases, we're getting a better and better approximate. We start off. Oops. Okay, we start off at just a constant 1, and as n increases, we go to better and better approximation to the exponential function. It also has an interesting property that if we drop from at any point along this function, okay, we at any point along this function drop a perpendicular to the x-axis, okay, then extend that the tangent line, okay, extend the tangent line to the intersection with the x-axis, then that interval always has length 1. So here are two examples. We drop from this point up here, a perpendicular to the x-axis, and then we consider the tangent at that point until it intersects the x-axis. And again, the distance between that normal and this extension of the tangent line is unit length. Fascinating, simple, basic, well not simple, but deeply important basic properties of the number e and the function e to the x. The other fascinating thing about the exponential function, y equals e to the x, is that its derivative, the change in y for a change in x, is, of course, this is the tangent of this slope of the line at this point. Okay? The tangent of that value alpha here, for example, is equal to y over 1. So the derivative of the exponential function is itself the exponential function. So it keeps, you can, a second derivative, third derivative, nth derivative, you always get the same result, e to the power x. Differentiating e to the x to any order of differentiation, you get the same result, e to the x. We'll need those properties in order to get to better understanding of the Fourier series and the Fourier transform. So here then are just, again, some illustrations of the behavior of the function e to the x, e to the I x, or e to the I phi, because we'll be thinking of both x and y components, e to the I phi, as we consider on the unit circle rotating a radius through all kinds of angles phi going around. Right? So we take, this is what we start with. E to the I phi is cosine phi plus I sine phi. We get that by saying the trigonometric function, the cosine of phi is x over r, but r is unit radius, so cosine of phi is x, sine of phi is y, so the projection of this radius onto the x-axis, projection onto the y-axis. We consider, what about the values going round the circle? On the argon, these diagrams with real and imaginary axes are generally referred to as argon diagrams. Argon was a French mathematician who also was concerned with the properties of complex numbers, and he found them most easy to deal with if he thought of them as on this complex plane with a real horizontal axis and an imaginary vertical axis. So if we go around 90 degrees, we get to intersecting the imaginary axis. So that's e to the I pi over 2. Phi now becomes pi over 2, and that has a value of I. Okay? Again, applying to this, say, the Euler identity. Put in for phi, pi over 2, then this evaluates to just I, because x goes to 0, and at pi over 2, x goes to 0, and y goes to infinity. Continuing on, we get halfway around the unit circle. So e to the I pi, that has there's the Euler identity. E to the I pi is equal to minus 1. And so on here, minus minus I pi over 2 and negative of I. So we have these quadrantal values, 1, 2, 3, 4, of the exponential function e to the I phi. So it's good to be able to fix in your mind and be able to recreate in a sketch when you're fumbling through trying to understand some of the expressions that are involved in the Fourier analysis of crystal structure, be able to recreate this diagram for yourself and not have to memorize, oh, e to the minus I pi over 2 is equal to the negative of the imaginary unit. So now we can be thinking about, for example, we thought about these quadrantal values of e to the I phi going around the unit circle on the complex plane, the argon plane. Think about what happens if we want to consider the negative of e to the I phi. That is, negative of e to the I phi, not the negative of phi for the moment, but the negative of e to the I phi. That's this radius vector that's just in the opposite direction. If we then want to consider e to the I negative phi, okay, that means the negative of phi is a rotation that is clockwise. Positive, conventionally positive rotations are anti-clockwise or counterclockwise. So a clockwise rotation corresponds to a negative rotation angle. So e to the minus I phi, well, in the Euler expression, comes down to cosine phi minus I sine phi, x minus I. So this is a complex conjugate of this, okay? Because I would just reverse the sign. And of course, it can then have a negative too. We take the negative of this quantity means radius vector in the opposite direction. So if we consider the negative of phi, that's this guy, that gives us this radius vector. But now to reverse it, we end up in this quadrant. Again, being able to recreate these pictures in your head or on a sketch paper is certainly better than trying to memorize all this stuff. after you do it a few times, of course, much becomes second nature. So this particular relationship between a complex number and its conjugate, the complex conjugate, is one that comes up often in the Fourier analysis in crystallographic applications of Fourier analysis. So you've got to remember that the negative phi corresponds to rotation in the clockwise direction as opposed to the anti-clockwise, counterclockwise direction. So the complex conjugate of a complex number z is in general not the extension in the negative direction. That would be the negative of the complex number. Complex conjugate is one is in this illustration, keep in mind, one is above the real axis, one is below, because the negative rotation corresponds to the negating the imaginary term. Using this kind of thing, this particular relationship between a complex number and its complex conjugate, that feature of complex numbers is a feature that allows us to deduce that even though structure factors are in general complex value, electron density is real value, and we'll show that in detail. But it depends in part on this relationship between the number, complex number and its conjugate. Well, this just re-illustrates some of what was on the earlier slide, but these kinds of relationships. One can often get confused in working through the algebra and working through some structure factor algebra, and it's good to be able to resort to a diagram like this, at least a diagram in your mind's eye, if not actually writing it down on paper. Well, this is something that we saw earlier in that film version, that in 3 dimensions we have a projection onto the real plane. That's the cosine, in this case the sine part. No, yes. The real plane is the one that includes the x-axis. So here's the cosine function, which is on the xz plane. We could imagine z being a real axis coming out of the plane that we've drawn. And then similarly in this is the sine function. If I don't get lost here, back up and down and around. That's a projection onto the y z plane, where y involves the imaginary unit. Engineers often use, for the imaginary unit, j instead of I, because their frequent electrical engineers are using I to represent current. So you'll encounter in some of your reading, the use of the symbol J for the imaginary unit, but more often than not, I. Okay, now to get to some further deeper properties of the exponential function, the trigonometric functions related to what we're doing in Fourier series. In Fourier analysis, you remember that, did we show this? I can't remember. No, we didn't yet talk about Fourier series as a series expansion, in principle, infinitely many terms. But this particular series, where we take, starting from some known value of the variable x, call it x naught, and we can evaluate, and a known value then of f at x naught. This would be a y value. Okay, we can construct at any other point, this series tells us that any other point along the x-axis, the value of the function there is equal to starting with the one point we know, and then multiplying, adding out these terms. Okay, here's a term in the first derivative of y with respect to x, but then evaluated at x naught. So here's what we mean by that, f prime of x naught. That is, we differentiate whatever the form of y, we can find the derivative of y, or imagine that we have the derivative of y with respect to x, but then we plug in the value x naught and get a numerical coefficient here to put in this series. Right? And that coefficient gets multiplied by x minus x naught, x the value we're seeking, and x naught the value we know, and then multiply that by 1 over 1 factorial, which is 1. Then we go on to the second derivative, right, and do the same thing, but now we multiply by the square of the difference between x and x naught, and then divide by 2 factorial, and so on, the cube of the difference divided by 3 factorial using the third derivative. And in general, for the nth derivative, the nth power of this difference divided by the nth factorial, and we sum over all those terms. Now, the case that's commonly used, that we will commonly use, is the simplification of this when we're talking about x naught having a value of 0. So then f of x is given by whatever the known value, f at the value of 0, so y when x is equal to 0. First derivative times x. We don't have to worry about the subtraction because x naught is 0. Then second derivative times the square of x divided by 2, and so on. So this one, this kind of specialization of the Taylor series, is so-called Maclaurin series. Here we're expanding, carrying out the series expansion by some general value, x naught, and here we're carrying out the expansion against x equals 0. So we'll need to carry out this expansion in order to get at some other properties related to Fourier analysis. Okay, so let's see if we can use the Maclaurin series, or the first order Taylor series about expansion about 0, to get a series expression for the cosine function, and similarly for the sine function. So we need all those derivatives, right? So the derivative of the cosine is the negative of the sine, and the derivative of the negative of the sine is the negative of the cosine. And the derivative of the negative of the cosine, we're getting down to the third derivative, is again the sine function, and the derivative of the sine is the cosine. Okay? At the fourth order derivative. So evaluating those guys, when x is equal to 0, we get 1, 0, negative 1, 0, 1, and it goes on this way in principle forever. So the cosine function can be, as a series, represented by this one. 1 minus x squared over 2 factorial plus x fourth over 4 factorial plus x, and so on. Okay? And the reason that we get only the even order terms here is that wherever the sine function turns up among these derivatives, its value at 0 is 0. Okay? So the cosine is this expansion in even powers of x. And you could imagine that the constant term here is x to the power 0 over 1 factorial. 1 factorial is equal to 1, and to the power 0, the x to the power 0 is unique. Okay, so we have the even expansion, even term expansion for the cosine, and by the same procedure, considering derivatives of sines and cosines evaluated at values, we get an expansion, a corresponding expansion for the sine function. It begins not with a value of unity, but with the value of x, okay, whatever x is now, and then goes out in terms of odd powers and odd factorials. So we have a series expression for the sine, a series expression for the cosine. They will turn out in a moment to be useful. We do this. Let's try to do the same thing. Instead of expanding the function sine and cosine, expand the function e to the x and e to the ix. So a real value function e to the power x, where x is a real number, and then the complex value, or imaginary value function e to the ix. Okay, so here's the Maclaurin series again, the various orders of derivatives, the various integer factorials. Evaluate the function evaluate these derivatives of the function e to the x. Well, we pointed out before, no matter how many times we differentiate it, we keep getting the function back. So any order, the derivative of nth order derivative of the function e to the x is equal to e to the x. And if we evaluate these derivatives, all of which are the same, at the value of 0, we get the same result for all unity. E to the power 0 is equal to unity. Okay, so now we can have a series expression for the function e to the x. And that comes to 1 plus x squared over 2 factorial, x3 over 3 factorial, and so on. So we have both even and odd powered terms in the expansion of e to the x. So if we evaluate those now at x equals 0, okay, so it just means the number e is equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. 3 factorial is equal to 6, 4 factorial is equal to 24, and so on. So when we sum up those factorial fractions, we get to 2.71828, and then the more of them we sum, the more digits we get in the expression for the number e. E to the ix, well, it goes in the same way, except that now the function in the powers in the numerator are the powers of ix squared, ix cubed, ix to the power 4, and so on. Well, x squared is equal, I squared is equal to negative 1, so this term, e to the ix quantity squared by 2 factorial, comes down to just negative x squared over 2 factorial. And similarly here, the cube of power, or the cube of I regenerates I. Okay? So you see how the powers of the imaginary unit go. And so we get this series in alternating algebraic sign with even and odd powers. Okay, so the odd powered, and it's not just series just alternating. It's not minus 1 plus 1 or anything. We have a period which is 4 terms long. Okay? 1 I minus 1 minus I. And then now it repeats if we go to higher order. So we have even and odd terms. We can separate them. We can say, okay, the first part of this, let's just collect all the even terms, even order terms, and then collect all the odd order terms. Well, what we recognize is this series expansion is the series expansion for the cosine function. This series expansion is the series expression for the sine function. So what we have said now, concluded, e to the ix is the cosine of x plus I times the sine of x. And then we have the beautiful Euler identity, okay, when x is equal to pi. This is the kind of way of things working out that gets people who have that kind of mathematical inclination in their head excited and happy. I never saw Herb Hauptman wet his pants, but he was actually quite excited about things like this happening. And he knew them. It was a crazy thing. So at the end of Herb's life, he was suffering from dementia quite seriously. But up until just, I'd say a week or two before his death, when he worked short days, he would be in the lab just for a few hours. But he and I would often have conversations. I would kind of draw him out to talk about the history of mathematics. He forgot none of that. His dementia did not erase any of his knowledge, which was an abundant knowledge of the history of mathematics, going back even before the Greeks. Gauss was his hero, everything that Gauss did. Even though Gauss was not a nice guy, Herb didn't care. Gauss was his hero. And similarly, Herb never forgot, he was a classical music lover, everything he knew about classical music was also at his fingertips in the deepest stages of its dementia. It was quite remarkable. It's truly unfortunate that you haven't had the pleasure of getting to know. Remarkable guy. Okay, so now we can talk about getting the Euler formula from the Taylor series. We have a cosine expression expansion, a series expansion for the cosine, a series expansion for the sine. We have a series expansion for e to the x, which gives us the value of e. And we have a series expansion for e to the I phi, which is this sum of even and odd terms. So here we have the cosine function, here the sine function, here we have the Euler formula. So another way to get the Euler formula. I don't know if this is what Euler himself was thinking about. I don't know anything like the history of mathematics that Herd knew, for example. But one way to think about getting at the Euler formula is to consider differential equations and given set of boundary conditions. Well, we know that if the function is e to the ix, then its derivative with respect to x is I e to the minus, I e to the ix, right, is equal to I times y. Right? Similarly, so this gives us this expression dy dx minus iy is equal to 0. Y of 0 is equal to 1. So if we consider the other side of things, the trigonometric expression, here the complex exponential expression, here the trigonometric expression, we do the same kind of thing. For now, let's call this function z. Derivative of z with respect to x gives us this trigonometric expression minus sine x plus I cosine x. And then if we multiply this expression through by I, then we get I squared times the cosine, we get I now factored out, cosine x plus I sine x. Right? So that's equal to I times z. The derivative, again, of the function, derivative minus the function is 0. Right. We get to the same conclusions by two different routes, considering the differential equations corresponding to the complex exponential side and the derivatives with respect to the trigonometric side. Yes, we can finish with this next couple of slides. So one of the very useful formulae, identity formulae from trigonometry are the expressions for the cosine and sine of the sum of two angles. The cosine x plus y and sine x plus y. Those don't just drop out by looking at the picture on the unit, on the unit circle on the plane. But if we think of getting at this kind of expression for cosine and sine of sum of two angles, well, we say that needs to be equivalent to e to the I x plus y. The laws of exponents are, we just can factor this into e to the ix, e to the iy. Okay? Because when we multiply exponentials, we sum the exponents. So by Euler's formula, this is the cosine of x plus y plus I times the sine of x plus y. That's on this side. Now, if we consider here e to the ix, we have cosine x plus I sine x, multiplying cosine y plus I sine y. So if we carry out those multiplications and combine terms and so on, we get down to cosine x cosine y minus sine x sine y plus this term in I, cosine, the mixed term. So we get the self terms and then the cross terms, the mixed terms. Okay, so this is the result we see. All right? We want to know about the sum of angles formula. So here we say the cosine of x plus y evaluates the cosine minus sine, and the sine of x plus y evaluates the sine cosine plus cosine sine. Right? And if we consider x minus y, similarly, cosine plus sine, right? So change the sign in the middle here, and the sine of x minus y, sine cosine minus cosine sine. So if we form this product, cosine x cosine y, it means it comes down to this result, 1/2 of cosine x plus y sine and so on. Similarly for the sine. So we come down to these results, that these mixed products, cosine and sine, or sine and cosine, evaluate to these guys. So we've ended up being able to come to the sum of angles trigonometric formula. If x and y are the same, things get simpler, because then what this comes down to is the square of cosine x, and that's 1/2 of the cosine 2x plus 1. So all of these identity results follow from using the Euler formula on seeking the sum of angles formula. So I think we'll stop with this one, just to exercise your minds a little bit and sharpen your appetite, so we won't skip lunch because it'll be delayed. So we want to have, as I said, because they turn out to be very useful, we will use them, the sum of angles formulas. The cosine for alpha plus or minus beta is equal to the cosine minus or plus sine, and similarly the sine of alpha plus or minus beta is equal to the sine cos plus or minus cosine sine. How to get this by plane geometry. So we imagine we're looking at a piece of the unit circle that's in, just for illustration purposes, the first quadrant. So we have a circle of radius 1, and somewhere along that circle we consider a point P. From P we drop a perpendicular to the horizontal axis. Call that point B. From the intersection along the radius vector, we define point Q by dropping another perpendicular, and that means that the included angle here is alpha, the same as here. So we started out considering alpha and beta. We want to know the functions of alpha plus beta, or then we have here these triangle constructions. Now, working out the Euclidean geometry, we have, of course, the OP is unit length, and OQ, 0 to this point, is the projection of the radius onto this direction, this far out. 0, or OQ, that's the cosine of beta, right? Here's beta, the projection of onto the direction of OQ gives the cosine of beta. And similarly, we get wherever it was, and PQ, okay, that is this perpendicular, is equal to the sine of the angle beta, and opposite over hypotenuse. Then we do the same kind of analysis considering the points OA and OQ, and we end up with cosine alpha and sine alpha, right, because those are projections of OQ along the x direction. So now we can add them up. We know something. We know OQ and PQ, and we know these ratios for giving us the sine and cosine. So if we say that the cosine of alpha plus beta, that's this, both of these angles, the cosine must equal OB, the projection, this piece of the projection onto the horizontal axis. Then that's equal to OA minus this little piece, BA. So on and so on and so on. We end up that the cosine of alpha plus beta is cosine alpha, cosine beta minus sine alpha, sine beta, cos cos minus sine sine. And if we go put in the negative signs, cosine of alpha minus beta, then we get cosine cosine plus sine sine. So the sum of angles formula could be worked out, and was worked out, before Taylor invented his infinite series expansion, before Maclaurin simplified the Taylor expansion by considering the expansion about point 0 rather than some other point x naught. And it could be figured out, the sum of angles formula could be figured out before Newton and Leibniz invented the calculus. This is a proof from Euclidean geometry. I don't know if it's diagrammed exactly this way in Euclid's Elements, but you can see that the principle is there in ancient mathematics. I think that's, we'll talk about rotation of axes next time. We have to worry about rotation of axes because that's going to get us to a very important application in crystallography of rotation translation searches. You've got data for your unknown macromolecular crystal. There's this piece of your molecule which is already of known structure, a sizable piece, let's say a third or more of your molecule consists of a structure that's known, and so you can approximate the intensity distribution from the piece of the structure from what's known. You can calculate that from the structure that's known, and then compare the intensity data for your unknown structure with that for the known structure, and the comparison involves essentially moving the intensity distribution, one fixed and the other moving, so it's a rotation, and it may involve a translation. Right? The rotation translation methods, far and away, those rotation translation methods are responsible for the huge majority of crystal structures that are macromolecular crystal structures that are being determined today. Because we now have a big enough database of known structures that there's a high probability that you can find a structure which represents, to a good approximation, a sizable piece of your unknown structure. And you deduce these things from sequences and so on. Okay, so everybody have a good lunch, good weekend. We have a little bit more mathematics to do on Tuesday, and then we'll actually get into Fourier analysis of crystallographic things.